In this video, we will be introducing the concept of valence bond theory. Let's start by looking at some of the reasons why we would need a new bonding theory. The theory that we have been using up till this point is Lewis theory. Lewis theory, which we use to make Lewis dot structures, generally predicts trends in properties, but it does not give good numerical predictions, as we saw for bond strengths and bond lengths. Lewis theory gives good first approximation of the bond angles in molecules, but it cannot be used to get the actual angles. Lewis theory cannot write one correct structure for many molecules where resonance is important. Lewis theory often does not predict the correct magnetic behavior of molecules. An example of this is oxygen, O2, which is paramagnetic, although from its Lewis structure one would predict that it is diamagnetic. Lewis theory relies on the particle-like nature of electrons as part of its explanation. The electrons are occupying space that is between the two atoms. And you can have two electrons that are occupying in that space. Valence bond theory, on the other hand, utilizes the wave-like nature of electrons, which is described by the shape of the atomic orbitals. So valence bond theory relies on the quantum mechanics to form molecules. The bonding in valence bond theory occurs when you have the orbitals, which are expressions of the wave functions, overlapping and interacting with each other. What we have here is a diagram of the interaction as a function of distance between two hydrogen atoms. So over here you would have the two hydrogen atoms, the nuclei, directly overlapping, and far to the right you have the two hydrogen atoms completely separated. So as the two hydrogen atoms come closer and closer together, they start interacting. That interaction stabilizes the electrons, and the overall configuration is lower in energy. It becomes more stable. So as they come closer and closer together, the pairing becomes more stable as they share their wave functions, as they constructively add, up to a point where you have the maximum attraction between the nuclei on one and the electrons on the other. This is the bond length, and the value between when you have completely separated your electrons and when they are bonding is your bonding energy. In valence bond theory, the bonds between atoms occur when the orbitals of those atoms interact to form a bond. So it is an interaction of the wave functions which describe the shape of the orbitals, which leads to bonding. The kind of interaction depends on whether the orbitals align along the axes between the nuclei or outside of the axes between the two nuclei. By that, I mean if we have our hydrogen atoms and they are coming together, the axes between the two nuclei in three-dimensional space, the line between them, that is the internuclear axes. You could either have an interaction of orbitals along the axes, or as we will see, this is not the case for hydrogen atoms, but other ones where you could have a p-type orbital. You have your p orbitals. If they are perpendicular to your axes, let's say the red line is your axes where things are interacting, you'd have two p orbitals. Maybe the axis is along the x-axis, and then you have the y-axis here for your p orbitals. They're interacting with each other, and you get some overlap between the two orbitals. So that's how they can interact outside the axes. When it is shown up here is an interaction along the axes. The axis is occurring between the two hydrogen atoms, and the overlap is along the axes between them. Valence bond theory uses those quantum mechanical orbitals as part of its explanation for why bonding happens. The valence electrons of the atoms in a molecule reside in quantum mechanical atomic orbitals. Those orbitals can be the standard s, p, d, and f orbitals, or, as we will see shortly, they may be hybrid combinations of these orbitals, where we are essentially summing together or averaging, for example, maybe s and p orbitals to get hybridized orbitals. A chemical bond results from the overlap of two half-filled orbitals, that is, two orbitals that each have one electron in them, and the spin pairing of the two valence electrons, that is, one electron is spin up, the other one is spin down. Or, less commonly, the overlap of a completely filled orbital with a completely empty orbital. The geometry of the overlapping orbitals determines the shape of the molecule. One of the problems that we quickly run into when trying to add orbitals together through overlap is that without making modifications to the orbitals, they would fail to predict correctly the bond angles that get formed. For example, if we look at H2S, dihydrogen sulfide, what we would predict is we take an s orbital from our hydrogens. Hydrogens only have one s orbitals. In order to form a bond from the overlapping orbitals, the 1s would have to combine with the half-filled p orbitals from the sulfur. So sulfur's valence electrons are fully occupying. So sulfur's electrons are occupying a fully filled 3s orbital, and then in the p orbitals, the 3p orbitals, one of the orbitals is fully filled and two of them are half-filled. So your hydrogen atoms, which have one half-filled 1s orbital, will interact with the half-filled p orbitals. If we assume that this first one, as drawn here, is the pz axes, then this would be your px and your py. So if we assume that the filled orbital is our pz, as is drawn here, then we could have this orbital here be our px, this one be our py. The p orbitals lie directly along the axes, meaning that the angle between your two p orbitals is going to be 90 degrees. So if you're trying to form a bond between your 1s orbitals through overlap and your two sets of p orbitals, you would predict that the bond angle in H2S should be 90 degrees because you're taking the p orbitals and bonding them with the s orbitals of the hydrogen. But, as we know, the H2S would have a bond angle of about 109.5, which is consistent with a tetrahedral geometry. So what we need to do is make modifications to the orbitals. This is what we will be calling in our next video orbital hybridization, or just hybridization.